Hi everybody, and welcome to the shed, where basically we just play around with stuff. Now there's a whole load of vertical wind turbines out there, and I thought I'd look at a few of my favourites. And the first one that we're going to look at is this. It's the Owind wind turbine that won the James Dyson Award in 2018. It's certainly an innovative piece of technology designed to harness wind energy in urban environments. Unlike traditional turbines, which typically require steady unidirectional wind flow to generate, the Owind turbine is specifically shaped to capture wind from any direction, and of course that makes it ideal for urban settings where wind patterns are often turbulent and unpredictable. Its spherical structure and unique design is the result of the research and creativity of Nicholas Orellana and Yassine Nourani, two students from Lancaster University. They say that their inspiration came from observing how hurricanes and whirlwinds move in a spherical pattern rather than a linear one, and this observation led them to develop a turbine that could capture wind energy from all directions. After that, everything went a bit quiet, as these things often do, but it didn't go away. The guys worked on it in the background, and they're about to bring it out as a product, and they're going to do that through a crowdfunding campaign, and of course that has led to a resurgence of interest, including with myself. So I had to dig around and I came up with their patent. And here it is US Patent 2021/0340950A1. And if we look at the basic structure, what we can see is just a tetrahedron. It's four triangles set against each other, so a triangular base pyramid if you like. And then there are these faces, face A, B, C and D, set in that tetrahedron to create the Owind. If we split them apart as in figure 5, we can see that they are just two triangles interlocking with each other. The big deal is what makes up those triangles, and it turns out it's actually two layers. The first layer is flat, as you can see in part A of the figure, with a slice out of one corner, and then those fingers B lie on A to create a channel for the wind. Then there's a cup C, which is like a conic section, over the top of those, and then we get a layer of fingers D overlaying with the surface E. And on the fingers D, what we've got is that the side nearest the arrow is smaller than the side facing the other way. So there are two key things to the Owind: the control of the wind direction using the channels in two layers, and the Venturi effect from making one opening bigger than the other. Face A and B differs from face C and D, but you make up those faces as seen in that diagram, and then you put them together as two triangles like this, and then you interlock the triangles with each other to form the Owind tetrahedron. And I did exactly that on Tinkercad to produce this, which is a copy of the Owind from that patent. And here it is printed off. Now in the bottom I put a steel bar because it has an axis of rotation, if you remember the patent, and that axis is through that section there and that section there. So there's a bit of 8mm steel bar, and the foot has two 22mm by 8mm by 7mm skater bearings in there, which is 608. So that's in the foot, so that drops in there. And then what we've got is a hairdryer. Now, this won't generate by itself. It's just a wind capture device. Of course, we need the actual generator to bolt onto it to make it a generator. But the whole thing about the Owind is its ability to capture wind from any direction and turn in one single axis of rotation. So we've got it here, we've got a hairdryer. What we're going to do is point the hairdryer at various bits and see if it spins in one direction or not. Okay, that was pretty cool, hey? It does what it said on the box, and it's no surprise if you think about it, because these are little fins directing the air in one direction. It's bigger one side, narrower on the other, so it's going to have only one axis of rotation. So it certainly does what it says it will do. Now, you might want to give a very close look to the product that they're actually launching, and you'll see there's been some significant design changes. One thing is the air no longer passes through on that top layer. It seems to be closed off. Now, I'm not sure if it's being redirected, but certainly it's being closed off from exiting on the other side of the ball. They've maintained those fins at the top and the bottom for the rotational direction of the air, but there's been a significant change that's worth a better look into and perhaps a play around with in order to discover what it is that they've done. Anyway, it may be that the true genius of the O-Wind has got very little to do with these. As I say, it looks like they're closing them off, in which case it's not much different to an ordinary Savonius. But the true genius could well be this section here, where it sits on the top. Remember, that section bows around to act like a little thrust, and that could well be the core of the turbine. Anyway, I thought I would run up a model because it's coming up again. There's been lots of reports on it, and some are claiming 700 times better than solar. Another wind turbine design that I think that is truly impressive is the Harmony wind turbine. Now, the Harmony wind turbine is based on the Savonius turbine, which was a Finnish turbine developed in 1922, and essentially it's just two scoops. And here's an example of it in a little wind-driven car we made in video 1967, I think. Okay, there it is, finished, and we've moved that. Obviously, then the rotor turns. Equally, if we turn the rotor, it'll move the vehicle. It's a ridiculous thing, isn't it? But sometimes you've just got to have fun. Okay, let's put a hairdryer on it. And it works by something called differential drag. So when the air hits that turbine, it hits the scoop and forces it round because there's more force here than there is drag on this curved section that's moving through the wind. And of course, that causes it to rotate and we have ourselves a wind turbine. It's a tremendously popular design because it is so simple to build. Now, commonly, they're thought of as being sort of 15% efficient, but recent research is showing that, in fact, they're around about 30% efficient or so. So there's been some changes in the ideas of this, but it was the inspiration for Christopher Moore's Harmony turbine. Now, I like Chris. He's an interesting guy. He came through OU Power, I believe, and Open Power Research in the 1990s and developed the wind turbine in, I think, the early 2020s, and then he's since dedicated himself to this. And his big thing, the thing that really makes this exciting, is that when you arrange the scoop blades properly, they're able to fold up on themselves so they can close in and move out depending on wind conditions. So the wind is low, then they're opened like that and they can capture more of the wind energy. When the wind is high, they furl to close together like that so they don't overrun. The effect of that is to increase the wind speed that they can actually operate in. Because when wind speed is too high, normally you have to shut other turbines down or they'll literally tear themselves to pieces. They spin so quickly. With this furling design on a Savonius, that doesn't happen because you can reduce the speed by furling the blades up. And that means the area or the time you can actually run a turbine like that is extended. Now, it's a beautifully simple design and very clever engineering, and that's what I really like about it, is the smart application of that engineering to a turbine design. So I drew this up in Tinkercad because I'm quite fascinated by the engineering, and of course I printed them out. And when you've printed them out, this is what you get. Now, I've decided to print these in two halves because it saves the infill there, but all you do is glue those together by matching up the two gears. When you've printed out four and glued them together, that's it, and there should be two of them with those knurled ends because they fit together like that. These are part of the driving mechanism that close them and open them. So what you need then are two of these. These have this bit facing the bottom because the whole thing actually drives the generator from this arm or this here if you like. So they're going to be that. Now that bit is a long cog which goes in the centre there, and we have a cog that sits on top of that because that's going to be driving it. So the wind drives this here, making it spin, the whole thing. But that bit sticks out, and the idea is to attach a small motor to that, and the motor will turn that cog, and that cog will drive these. These go in the side pinion arms, like that, and that is where these two fit on. So that fits on like that, and that fits on facing the opposite direction like that, and then we put this top plate on. When it's together, that's what it looks like. Obviously in that open position, when you've got a low wind, it's going to spin relatively quickly. But what happens is this armature here is connected to these driving arms, and of course that's down to the generator, which is taken from that short stub section. When the wind picks up, what you do is attach a motor to here as a control motor, which will turn that cog, and of course that puts it into the closed position. And it can close up for any wind speed gradually, allowing you to adapt it to the wind speed. Now, this is just a single unit. What Chris has done obviously is stack those units together, so you get a whole stack of units, one on top of the other, to create a helix. That helix is another, well, I think quite cool innovation relating to this type of wind turbine. Now, it is under patent, it's under investigation. I think Penn State are working with Harmony on this to have a look at it, and there's some very good results out there, and results are really what you're interested in. So I'm not going to release these STL files, but the drawing was actually relatively simple, and for me there's more work to do on this, but I thought I would show you the basic design, how it works, and that it is quite a promising wind turbine, and I love it just because of the engineering. So there are a lot of ways to classify wind turbines, but perhaps the two most popular are what we call the horizontal axis wind turbine and the vertical axis wind turbine. Now, I'm a huge fan of vertical axis wind turbines, or VAWTs, and of those there are two really popular types, and that's the Duraeus type and the Savonius type. Now, Duraeus types, well, there's only 3 of them, and for the Savonius types there's essentially 4. Now what you normally see, of course, is a wind turbine in that direction when it's a vertical axis, and this is a Savonius type, which is just 2 scoops and works by differential drag. So the wind blows in here, turns it, and there's less drag on this surface, so it always turns in that direction. And you quite often see them in that orientation, because there's nothing to change if you put it in that orientation. And there's lots of suggestions to put this kind of wind turbine along things like motorways to pick up the air from the traffic, or the moving air from the traffic, make it rotate and use that as part of the smart motorway program. Because that orientation does differ, and when it's in that orientation it's more commonly known as a cross-flow wind turbine. Crossflow wind turbines, you might recognise them more actually from something like this, which is a squirrel cage rotor. This you'll find in things like air conditioning fans, blower units, that sort of stuff. It was actually invented in 1891 by Paul Motier with the French patent number 215662 and registered in the United States. The main purpose was to utilise it for mine ventilation, but it was overlooked. However, there was a re-emergence of interest in the late 1920s and early 1930s with a variety of industrial inventions in different applications, such as drying grain, air conditioning, which came in round about there, and the injection of pulverised fuel into furnaces. It was also used by Anthony Mitchell, who designed the Crossflow hydro turbine in 1903, and Donat Banki, who founded this theoretical approach in 1922, and that made it known as the Banki-Mitchell turbine. At the same time, Fritz Osberger developed Mitchell's design and patented it, and therefore that kind of turbine is mostly known as a Banki-Mitchell turbine and an Osberger turbine, and it's one of the main varieties of cross-flow used in hydro. It was in the early 21st century when several researchers suggested that the Banki-Mitchell turbine could be used to absorb wind energy as a cross-flow wind turbine. Now, cross-flow wind turbines look like this. They're an arrangement of blades around the circle in a module, and these modules can be stacked as long as you want. And usually the blade number is somewhere between 6 and 24, although research has suggested 16 as being the ideal number, although there is argument, and people have suggested things like 6, 7, 8, 20, 22, all kinds of things. But 16 is supposed to be pretty good. And when they stack them like that, of course, they put them in a case, and normally there's a wind deflector around them to keep the wind in the right place and deflect it where you want it to do its work. So the main advantage of it is it'll start at really low wind speeds, cutting in as low as 2 meters per second, and so it's an excellent candidate as a self-starting turbine. It has low noise, remarkable stability, and its general approach makes it ideal for use in urban areas. It's a simple structure, and so there's low maintenance costs, and it's not as dangerous for flying birds as HAWTs. However, the power coefficient is quite low. It's 0.12, though that can be improved by adding augmentation devices. It also has a problem with high wind speeds, and it's not recommended to go more than 20 meters per second, and so you'd need some kind of braking system. So mechanical brakes or electromagnetic brakes, or a combination of the both of them, so that you would sense the wind speed and brake the turbine, because they are made of lightweight materials, which is part of what keeps the cost down, but they can't really stand those high wind speeds anyway. Augmentation devices are going to be things like guide nozzles or guide vanes, the casing itself, windshields, deflectors and cowlings, and you see those in things like the power pod, for example. In terms of the RidgeBlade, you can see that the rooftop that you're recommended to sit it on is acting as a very big deflector. Now, everything has an impact on a wind turbine, but the key design parameters are actually only really 4 of them. The first one is obviously the blade profile. Now, originally, they were just half a circle, so they were just that shape, 180-degree part of a circle, though, of course, these days, what's coming in are airfoils. So, the shape of the blade, the number of the blade we've already talked about, and where the blade is angled to an imaginary line drawn through the centre, and it's recommended that the angle be about 45 degrees or so. And the final one's a little bit surprising. It's the ratio of the thickness of the blade to the size of this diameter of your rotor, and it's recommended to be somewhere between 0.53 and 0.78 as a ratio to give the right thickness of those blades for it to act as a wind turbine. So I appreciate that's a lot of information to give on the history, design, use and some of the parameters of a Crossflow wind turbine. And that's because 2 reasons. 1, the RidgeBlade is a Crossflow wind turbine. And 2, when I did the research for this video, there was a surprising lack of available information. Plenty of really nice advertising explaining how it all works, but not much in the way of how it performs and why it performs. Now, RidgeBlade are a small company. They don't sell directly to the consumer, and so they, I believe, get overwhelmed quite a lot, so fair enough. But it is an exciting looking thing. Now, Crossflow wind turbines are not the most efficient, as we mentioned in the video, but I don't believe that getting on the 1 horse of efficiency is the answer. There are always other considerations to take into account. So you're thinking about things like the look of it, the environment that it's in, the urban environment, the cost of actually putting it up there. All that sort of stuff will come into play when deciding on a wind turbine. Now, a great part of the wind turbine cost is the structure you stick it on. And a great advantage of the RidgeBlade is the structure's already there. It's your house. And so that's going to reduce the cost dramatically because you don't have to build a tower. So when people say, oh, it's such and such and you should only do that, then they're not really considering the whole range of what needs to be done. I mean, the RidgeBlade is, and like all Crossflow turbines, very quiet. And that's important in an urban environment where you don't want the whiz, whiz, whiz of a standard turbine. Another thing very much in favour of Crossflow wind turbines is they work very well in that height range of 0.5 metre to 10 metres off the ground, and very well in that wind speed range of 2 metres to 20 metres per second wind speed, and of course that makes them a very good fit for an urban environment and a domestic use. I certainly would consider getting one if the price was right. So spirals, well, they're absolutely everywhere in nature, from galaxies to sunflowers, wave formations and wind types. But really, surprisingly, there are only really 4 types, and they're the Fibonacci spiral, the logarithmic spiral, the golden ratio spiral, and the Archimedes spiral. Now, mathematicians will hate this, but from an engineering build it and see what it does point of view, you could say that the Fibonacci, golden ratio, and logarithmic were in fact pretty much the same thing, which would break them down into two basic groups. Now, if you want to know more about spiral formation, the mathematics behind it, there's a chap called Zeroth who's done a brilliant video on it, and I'll put a link to the end of this video and a link in the description to Zeroth's video if you want to jump over there and get a better understanding of how spirals are actually drawn and framed, and a little bit about the history of the mathematics behind it. But I'm of a more practical bent, of course, and what I want to explore is how spirals have been used in wind turbines. Now, the simplest wind turbine is got to be the Savonius. It's basically two cups that catch the wind, and there's a difference in drag, and so they spin. And the first thing that was looked at was that, and it came up in this paper. So what the team did was take a Fibonacci spiral and use that as the inspiration for the Savonius type blade. And they tested it in lots of configurations, so overlapping gaps, matching gaps, 2, 3, 4 blades, and they found that the best configuration was with 2 blades and no gap in between them. And they ran a series of tests and came up with the result that it had an improved power coefficient of 14.1%. Of course, this spread like wildfire, and you found people doing turbines, Savonius type turbines, in that configuration all over the place. Of course, that sort of stuff always inspires people, and in 2018 this paper came out. What this team did was to construct a conical spiral, and they did that by taking the Fibonacci spiral, laying it on a flat piece of paper, cutting it out and rolling that round to make part of the cone. They repeated that 3 times and put those blades together at 120 degrees to come up with their conical spiral wind turbine, which they then promptly tested, of course. And the results were truly astounding. They got 73.1% with an idea that they should be able to get up to 80% of the power extracted, the available power extracted from the wind, and that's, well, it's phenomenal when you think about it. Equally, that went around like wildfire and is the inspiration from the Liam F1 wind turbine, which everybody's talking about at the moment, and for replication efforts, including one by myself. It'll be, so it should be, set on a pole like that. That's 0.9 meters a second, and it's actually starting to turn. .6 meters per second. Now, we did some generation testing back here at the lab and got some pretty good results. But if you want full build details, they're in video 1998, and I'll put a link to that at the end of this video. I 3D printed mine, of course, because I've got 3D printers. But if you follow that research paper, then you could use the same procedure of laying out a flat sheet and rolling that sheet up into the cone if you wanted to make one if you don't have a 3D printer. One of the things that's quite astounding about this spiral turbine is it's one of the first ones to make it out of the research lab into actual product, which is what the Liam F1 is, because so often these things just stay in the papers. When they actually get out there, that's a bit more inspiring. Now, both the papers I've quoted in this video are open access. It means they're not behind a paywall. Anybody can go and read them. And if you go to Google Scholar and put in spiral wind turbine, you'll find that there's a ton of corroborating research now to show that these spirals actually are worth pursuing. Now, sometimes you'll find them called an Archimedes spiral. I mean, they're not. Okay, they're a Fibonacci spiral usually. I guess it's some kind of nod to the Archimedes screw, but they are still a spiral turbine, and there is an awful lot of it out there for people to have a look at and judge for themselves whether they're any good or not. So with the exception of hydro, it's a well-known thing that renewables, so wind and solar, are generally more expensive than conventional generation. It's supposed to reverse somewhere between 2020 and 2040. However, when have you ever known a projection to come true? It's a little bit of a no-brainer that if all you're interested in is the energy, well, go buy a generator and pour something in that you can burn. For renewable energy, it makes it a much more difficult job. It's a bit like a salmon swimming upstream. You've got to have other reasons for wanting renewable energy apart from just generating energy. And you can understand why that would be the case. I mean, you know, a wind tower, it takes tons of concrete, gallons of fiberglass. That fiberglass is going nowhere for 100,000 years. Solar is very intensive. It's a strip mining operation, purification, energy intensive, lots of pollutants and relatively expensive. So there's lots of things really operating around it that makes that the case. Thankfully, there is an alternative. Now, nobody really knows where kites came from, although they can be located in Asia. The Chinese claim the first kites in something like the 5th century BC, but the earliest known depiction of a kite was around about 9,500 to 9,000 BC, making them somewhere around 1,100 years old. It was the Munai people who actually still use this style of kite that developed, that painted that cave painting, and that cave painting can be found in Muna Island, southwest Sulawesi, Indonesia. From there it's thought to have moved to China, and from China, of course, it moved to India. The Chinese used the kite for a whole host of things, including measuring distances, wind speed, travel, military communications, and they have said to have lifted men with kites. In India, they became famous as the fighting kites, and it wasn't until around the 13th century that Marco Polo brought the kite back to Europe. The kite in Europe was first recorded as a drawing, I believe, in about the 1800s, and of course the 19th century it was used by the Wright brothers to measure wind speeds and enjoyed something called the golden age of kiting. They lived about the period from 1860 to 1910 across Europe, and they're still used today, obviously, for things like scientific measurements, and there's been a whole host of kite developments, including the Eddie's Tailless diamond kite, the Rogallo wing, the sled kite, parafoils and power kites. So kites have an extraordinary long and illustrious history. It wasn't until about the 1970s when Lloyd suggested using kites for power generation, and he did some early experiments then. Unfortunately, of course, there wasn't the electronics to control the kites nor the materials available. That has all changed, obviously. Now, kites can only really operate in two ways in order to generate power. One way is to lift them, and as they lift, drag a rope which is wound round a drum, and that operates a turbine. When you get it to its height, you can change the pitch and it will literally drop to the ground. When it gets low enough down, you can change it again and it will fly and pull that drum, and that's one way of generating energy. Another way is to make them go around in circles, and as they go around in circles, they're tethered to the ground and they can run a generator because they're rotating. There has been a huge growth of interest in kite-based generators. In 2017, there were something like 60 companies involved and research institutes in kite-based generation. And what's cool about kite-based generation is it's scalable, both up and down. So it can go from megawatt scale industrial kites that have been developed by larger companies to even smaller systems like the one by Rob Reed on the Isle of Lewis, where he basically uses a kite to lift his kite-like structure that rotates in the wind connected to a bicycle wheel connected to a generator. And Rod claims that he can charge his electric car, he's got plenty of energy to boil water. So a very successful smaller scale which the individual could build, and of course that always appeals to me, because it's great to look at what companies are doing and what the future might be like for mass generation, but it's also great to be able to do your own thing and to generate at a scale that's reasonable at home. The reasons really that kites are so interesting is their lack of structure. Now, it's without a doubt that kites have had a bit of a shaky start, and airborne wind energy is slow in taking off, if you pardon the pun, but numerous companies are developing technologies such as large kites that can harvest wind energy up to half a mile above ground, and while it's still in its early stages, airborne wind power could potentially be used in remote locations or flying from barges offshore. In 2022, the German company SkySails Power launched a wing over the beaches of Mauritius, and although it only generated about 100 kilowatts, typically enough to power 50 homes, which is just a tiny fraction of the island's demand, SkySails see this as a sign of the future. Because as the world heads towards net zero emissions, pretty much every pathway for future electricity production foresees a big role for wind. The International Energy Association forecasts wind energy skyrocketing 11-fold by 2050, with wind and solar together accounting for something like 70% of the planet's electricity demands. Thanks mostly to the expanding number of wind turbines dotting fields and adorning ridgelines worldwide, the cost of wind has plummeted by about 40% in the past decade. But some wind experts say that those massive turbines aren't always the best solution. They can be expensive or logistically impossible to install in remote locations or deep waters, and just can't reach the lofty heights where the wind blows the hardest. To harvest these spots, it may well be that flying a kite is the answer, and that's why dozens of companies and a handful of academic institutions are now investigating a plethora of airborne options. And as we showed earlier, Rod is giving a very fine example of a DIY version that you can basically put together yourself. So triboelectricity is that electricity you get by rubbing things. Tribo is great for rubbing. It's also the electricity you get just by touching things. When you touch things and rub things, you transfer electrons and you create a potential difference, and you create energy doing that. It's the same kind of energy you get when you rub a balloon on your jumper and you can stick it to the wall, or you stroke a cat too much and polystyrene will stick to the cat. All of those rubbing actions that you can get in different materials will create electricity, and that's astonishing if you think about it. That's the same kind of energy that we've been looking at when we've been looking at this raindrop generator. The raindrop generator doesn't only work because there's already a potential difference in a raindrop, or from the kinetic energy of it striking the actual surface, which is part of it, but also the rolling down and rubbing of the raindrop on the surface. All of this creates a charge that our little structure collects. And the amount of charge that it can collect obviously is astonishing, and that's the way it is with triboelectricity. Previously, the issue with it has been that it's not very much and it's hard to collect, but the amount of research gone on in it is so vast that huge strides have actually been made. Now, when we made the raindrop generator, people were saying, yeah, well, it doesn't rain everywhere, so it's only useful in rainy countries, and that is very true. And the question is, what about wind? Can we do it with wind? Well, the answer is yes. If we can arrange something to rub, then it will create electricity in the wind, because the wind is doing the action of rubbing. There's two ways of doing this, obviously. One is to make the whole thing flutter, and as it flutters it rubs together, and the other is to have two rotating surfaces that rub against each other. And both of those ways have been explored. Perhaps the fluttering way actually is one of the most simple. There was a brilliant project done by a group of Canadians called the FLAG project, which I think stands for Flexible Linear Aerostatic Generator. It was basically 3 layers of plastic strung together, rub in the wind, attached to this circuit, and the circuit, as you can see, contains a variable capacitor in the centre, which is 3 layers of plastic. Then there's a rectification circuit, and then there's a load. And what the Canadians did was attach this to fluorescent light, take it outside and hold it up, and they could light the light with this tiny little generator. That in itself is hugely impressive. But of course, the wind bar is one of those things that just vibrates in the wind, and if you know the wind bar, it's a piece of material with 2 springs and a bit of electromagnetic induction going on. The bar vibrates, so you can have a string where the string vibrates when you're thinking about things like an Aeolian harp, or you can have a band and you have the wind belt where the band vibrates. But that vibration of a band in the wind is a well-known phenomenon. If we do that with 2 different materials like PTFE and Kapton, we generate a very high amount of charge and current, and of course that has been done, and there's lots of these TENG generators kicking around and demonstrating on the net, vibrating in the wind and generating enough power to light 1 billion LEDs. I'm joking, it's a couple of hundred LEDs. So that vibration in the wind can be accessed really easily, and it can be accessed at very low wind speeds indeed. But of course you can have it on 2 rotating discs, and simple rotating devices have also been come up with where, because there is no electromagnetic component, the amount of friction is exceedingly low, and so the wind speeds at which this can work are also exceedingly low. We have 2 discs of electrodes arranged with a small gap, and they spin in the wind with the little bits of plastic rubbing on each other. Bit of rectification in the way of that circuit I showed you for the flag generator, and sure enough we can create a whole lot of energy that does some useful work. And you've got to remember that these things are lab based at the moment. There's no production side to this, and so they use some relatively esoteric materials, and you can get some complicated structures going on where the power produced actually is significant based on the complicated structure of the esoteric material being used. Now, does that make it out of our reach? Well, I think not. I think our challenge, like we did with the raindrop generator, is to translate those academic papers into everyday materials. And sure enough, we're not going to get the kind of performance that you get. You're going to get an acceptable level of performance that we give up because we're using exceedingly simple methods and exceedingly simple materials to create our generators. But we have the advantage of scale. A lot of these things are a few centimetres across. We can build meters across and still have that power output, and so get considerable power from those. Now, I think this moves us away from the traditional style of wind turbine. When you think about the VAWT and HAWT, which is basically a great big mechanism stuck on some gears on a motor, with all its expense and difficulty and problems of maintenance, to things that come down to printing on plastic. I mean, we've put a layer of aluminium on some plastic, painted on some ink, painted on some varnish, and created ourselves a generator. That's only a very small step from being able to print these things. Silkscreen printing would do exactly the same thing. So the ability to create large scale using simple materials is suddenly within our reach, courtesy of the research that's been going on. So it's well worth having a look on Google Scholar. Now, Google Scholar is really simple to get to. If you go into a Google main screen, type Google Scholar, you'll come to a special section of Google which only has academic papers. If you type TENG, which stands for Triboelectric Nano Generator, wind, you'll come up with some of the most astounding things that people have been up to based on those 2 models I was talking about, either rotating or flapping. And you'll see that they've been up to all kinds of things. Now, sure enough, some of those papers are behind paywalls, but quite a lot of them are actually open access. You can just click on them and read them, because this is an area of huge interest to everybody for very obvious reasons. Now, I don't think it's going to overtake traditional wind generation in the next 5 years, nor do I think it will always overtake it, because there is not one size of shoe to fit all people. We need different shoes because people have different feet. We live in different situations. I'm in England where it rains a considerable amount of time. Maybe I was in Oregon or the South Island of New Zealand or in the Amazon. We get a huge amount of rainfall, and so a raindrop generator is particularly interesting. Some people live in high wind conditions where a traditional wind turbine works brilliantly. Some people live in low wind conditions where you need to harvest small amounts of wind. So there's just this huge range of conditions in which we live that different solutions are going to be appropriate. And exploring those different solutions is how I think we're going to solve our energy crisis. It's by exploration of these new ideas, by working together, by trying things out, that we're actually going to get an answer. I don't think there is one answer for everybody that's going to suit across the entire world and all the living conditions in which we live in. But I was asked if this triboelectric generation scheme that we're using for raindrops could be translated easily into wind, and the answer is yes, and it offers a new opportunity, a new direction for wind that really has only just begun to be explored in the last 5 or 10 years. There aren't any, as far as I'm aware, commercial applications of this out there, but all that means to me is there's an opportunity for us to develop our own applications and maybe make commercial applications out of it. Anyway, I hope the video was of interest. I hope it inspires you to look at that thing, but it is a little bit of a rabbit hole, as somebody actually mentioned on one of the comments. Once you start getting into this, then there is a lot behind it, and it can be a little daunting. I think what you need to do when you're looking at that is choose your direction. We've chosen for the while we're working on raindrops to work on raindrops, but we could equally choose to work on rain, in which case we might make a choice between the rotation and the flapping. If you think there's a best option, there isn't. Just one of those options will most suit you for your circumstances, and that's the one you should explore. There is never any such thing as the best and most perfect. There's just things that will do a job within the limits of what you want them to do, and they're suitable to the situation in which you're in. And I mean how you live, how much money you've got, how much time you've got. So all of those situations. Anyway, I hope you enjoyed the video. I hope it does inspire you to have a look at this TNG generation as a viable alternative to wind generation and as a thing to explore. Oh, just to add, the way of gathering this stuff is to stick it in a capacitor and use that capacitor to charge a battery bank. Anyway, I hope the video is of interest. I hope it was useful. Thank you very much for watching, and please remember to like and subscribe.